this video, I'll show you how to solve the ALEKS problem called Interconverting Wavelength, Frequency, and Photon Energy. In this problem, it looks like all the versions of the problem are pretty much the same. You're going to be given a specific amount of energy required to break a bond, and it wants you to calculate the wavelength of a photon that would be capable of breaking that bond. The equation that we're going to use to solve this problem is E equals hc over lambda. This equation gives us a relationship between energy, which is the number that's been provided to us, and wavelength, which is what we're being asked to calculate in the problem. In this equation, both h and c are constants. Now, since for this equation, since we know E and h and c and our unknown is down here in the denominator, the first thing that we should do is just do some algebraic manipulation on this equation to get that unknown variable in a better position. So I'm going to start with cross multiplication, and I'm going to rewrite this equation as E lambda equals hc, and then I'm going to rearrange it one more time to solve for lambda. Lambda equals hc over E. Now, as I said, both h and c are constants. H is Planck's constant, and its value is 6.626 times 10 to the negative 34. The units are joules times seconds. C is the speed of light. That we're going to use that as 3 times 10 to the 8th meters per second, and E is the energy, which is being provided to us in the problem, and it needs to be in units of joules. So one of the things that we're going to have to do is adjust the units on the value of energy because it's been provided to us in kilojoules per mole. And when we solve for lambda, that is going to give us the wavelength, and it is going to be in units of meters, and we're going to have to do a unit conversion on that as well. So let's start by getting our energy converted into the right unit so that we can plug it into the equation. For this problem, the energy that's provided to me is 238, and the units are kilojoules per mole. And that specifically is talking about the energy associated with breaking a bond. So when it's talking about moles in this equation, it's talking about moles of this particular bond. I'm just going to write moles of bonds. Now, in this equation, or sorry, in this problem, it's asking us to calculate the wavelength that would break just one single bond, not a whole entire mole of bonds, but just one. So the first thing that we need to do is change this unit from moles of bonds, or a mole of bond, into just one bond. We do not want to have the unit moles of bonds. Instead, we just want one bond. And we know that a mole is just a unit of quantity. 1 mole of anything represents 6.022 times 10 to the 23 of whatever it is that we're talking about. In this case, we're talking about bonds. So setting the equation up this way, we're going to cancel out that mole of bonds unit, and we're just going to end up with units of kilojoules for just one individual bond. We'll do the math on that. 238 divided by Avogadro's number, 6.022 times 10 to the 23rd. That's going to give us 3.95 times 10 to the negative 22, and that is kilojoules per bond. Kilojoules per bond. Remember that in this equation that we're using, our energy needs to be expressed in joules, not in kilojoules. So we're going to need to do one more unit conversion here, where we convert from kilojoules into joules. One more unit conversion where we want to cancel out kilojoules, convert into joules. Kilo is the prefix for 10 to the 3. And that's going to give us an energy of 3.95 times 10 to the negative 19 joules per bond. So now we're ready to plug everything into this equation right here that we're using. Lambda equals h, which is Planck's constant. I've got that right there. 6.626 times 10 to the negative 34. The units are joules times seconds. Next, we have c, the speed of light, 3 times 10 to the 8th meters per second. And then we're going to divide by the energy in joules, which we calculated as 3.95 times 10 to the negative 19 joules per bond. Let's take a look at how our units are going to cancel. The joule units will cancel, the second units will cancel, and we're just going to end up with the unit of meter or meter per bond for this wavelength. So I'm going to carry out the math on this. 6.626 times 10 to the negative 34 times the speed of light, 3 times 10 to the 8th, divided by 3.95 times 10 to the negative 19. And I get a wavelength of 5.03 times 10 to the negative 7. The units are meters per bond. I'm just going to start writing meters. And remember that the problem wants us to express this in units of nanometers. So I need to do one more unit conversion. Get rid of the meter unit, convert into the nanometer unit. Nano is the prefix for 10 to the negative 9. That means 1 nano is 10 to the negative 9. So I just need to take my answer and divide by 10 to the negative 9. And I get 503 nanometers.